Vanakkam. Welcome to this video on biomechanics. In this video, we will be introducing some basics of mechanics. We will start with an introduction to vectors and how to resolve vectors. So, this is introductory mechanics in statics and dynamics. So, in this video, we will be starting with mechanics, forces acting on a body. What are the types of forces? What is principle of transmissibility? How to resolve forces, and a couple of simple examples of how to resolve forces. So, we know what is force. Force is an external agent that is capable of changing a body's state of rest or motion. That is, if the body is at rest and if you would like to move that body from rest, you need to apply a force. Or if the body is moving and you want to stop that body from moving, then you need to apply a force to stop it. So, it is that agent that is capable of changing the state of motion, state of rest or motion. We know from high school that F is ma. This is the Newton's law, that is, the force is mass times the acceleration. Note that acceleration is a vector, just come to that in a minute. So, force F is m times a, m is having unit kilograms, acceleration is having the unit meter per second squared. The SI unit of force is Newton, which is equivalent to moving 1 kilogram mass with an acceleration of 1 meter per second squared. So, that is kilogram meter per second squared. The SI unit is Newton. This is the SI unit. In this equation, the acceleration is a vector, force is a vector. Force can exist in 2 dimensions or 3 dimensions. For the purpose of this course, we only deal with forces in 2 dimensions or the planar case. But in real life biomechanics, you almost always have 3D forces or forces that are acting in 3D. So, when you say force is a vector, that means that it has a magnitude and a direction. So, all the things that all the rules that apply for vectors also apply to forces. Types of forces: you apply a force on an object or a body, this is the applied force. Then you stand and the ground is applying a force on you, which is why you are standing still. You are almost always never standing still, you are always fidgeting. There is a little bit of oscillation that you are making as you are standing. It is a small movement that you are making. Let us take a table, or in this case this walker that is taken, and this walker is kept on the ground. It has 4 legs and it is standing still. Other than the vibration of the building, for example, otherwise it is standing still. Now, the weight of this walker is acting through these 4 legs, not necessarily equally. If it is a symmetric design, you might expect that to be equal, but not necessarily equally. Now, because I know that this walker is not accelerating downward, it is not just going down, I know that the ground or the floor is applying an equal and opposite force on the walker. This is why the walker is in static equilibrium. So, this force that is applied by the ground on that walker is called reaction force. Just like when you are standing still, your weight is applied through the feet on the ground and the ground is applying an equal and opposite force on your feet. This is the reason your feet are not going down, you are not accelerating downwards, right. So that force is called reaction force. Specifically when the ground is applying this force on your feet, there is a special name for it, that is called as a ground reaction force in postural balance, and while analyzing gait and walking, we call this force as ground reaction force. Okay. So that is the reaction force. Consider this lady, she is holding a ball. Let's assume its weight is 50 newtons. Okay. So she is holding a ball weighing 50 newtons. So that weight, because she is on planet Earth, is acting in that direction, is it not? That direction. But the ball itself is not accelerating downwards. Acceleration due to gravity is acting on it, but the ball is not accelerating downwards. Why is that? Because someone is holding it, like I am now holding this pen. Why is the pen not going down? Because I am holding it with my hand. That means I am applying an equal and opposite force on this pen so that it does not accelerate. Suppose I were to suddenly remove my hand, what will happen? Let us see what will happen. So that is, it is there like this. Suppose I am removing my hand like this, what happens? There is an acceleration that happens. I am just holding this thread so that the pen will not fall down and the instruments will not be disturbed here. But you see what happens. Suddenly I am removing this. That is the acceleration that you are seeing here. That means the reason why this pen is in equilibrium is because this hand is applying an equal and opposite force on this pen so that it remains in equilibrium. Okay. So this 50 Newton force is applied by this lady or her hand on this ball, that is why it is in equilibrium. Okay. This force that is applied by her, by this hand on the body, can be considered to be a active force or reaction force depending on how you are looking at it. Okay. Because you might look at this from the viewpoint of the ball or the hand. If you are looking at it from the viewpoint of the hand, then the force that is applied by the lady is the applied force and the ball's force can be the reaction force. But generally it makes sense for us to consider this force as the active force and the force applied by the hand on the ball as the reaction force. Okay. This is the reaction, because if there was no ball, then this force will not be applied. Okay. That is the reaction force. Likewise, here is a cart that is moving on a rail. Similarly, there will be some normal reaction force. Critical to note the use of the word normal. That means these forces are only acting normal to that cart, okay, not in any other direction. Okay. Then you have force in a spring. We know this from high school physics. Let us say that the spring is having a constant of K. The force in this spring is proportional to the deformation or the displacement that this spring undergoes. So I know that this force is Kx, right. One more thing that we know is the action of gravity. I have explained that in a previous example. One other thing is the so called frictional force. This is essentially a reaction force to the applied force, except it always acts in a direction opposite to that of the applied force. So here what is shown is there is a block on a table or on the floor that is being pulled or pushed in a particular direction. Right. So that is this force shown in red, let us call this 100 Newton force being applied on this block, for example. Now because the surfaces of the block and the table are rough, are not smooth, because of this reason there will be a force that will oppose motion of this block on the table. That force will always be opposite to the direction of the applied force. That means if the applied force is not along this red arrow, that means if the applied force is not along the red arrow shown but rather along that red arrow, then the frictional force will be along this direction. So it always acts against the direction of the applied force. It's a reaction force that is developed when this kind of surfaces are involved, in particular when the surfaces are not considered to be smooth. Most practical surfaces are not smooth. So in this picture, the red arrow indicates the applied force on this block. What does the blue signify? The blue force is the force that is normal to the block. This is the force that is going to overcome gravity. Let us say this block is having the weight 1000 newtons, then because this block is not accelerating downwards, this table or the surface is applying a 1000 Newton force in the upward direction, that is shown in blue here. This is the normal force. The frictional force is shown in green here. This is the frictional force. This is a tangential force, that is acting tangent to the surface, which is why it is called tangential force, but we simply call it as frictional force. How do we know the direction of the frictional force? It is always opposite to the direction of the applied force. Depending on the direction of the applied force, I will decide the direction of the frictional force. Some details are missed out here. The magnitude of the frictional force vis-a-vis the magnitude of the normal force will give us an idea of the amount of friction, for example. The angle at which the resultant is acting will give us an idea of the type of friction that is happening and the amount of friction that is happening. Some details I am skipping here, but for the purpose of this discussion, this is sufficient. These are the various types of force, some types of force that we discuss. There are other types of forces that we will not be discussing here. This is expected to be sufficient for the purpose of this course. Okay. One important principle while dealing with forces is the principle of transmissibility of forces. What is this? This is the idea that I could change, I could move the point of application of force along the line of action of force without changing any other analysis or any other factor in the analysis. That is, let us say in this case force F1 and a force F2 are acting at this point O. Now I know that the line of action of force is along that line. The line of action of this force is along this line, right? Now I can move this F1 to act from this point and F2 to act from this point without changing the analysis. This principle is called as the principle of transmissibility of forces. Important that you cannot move it anywhere you want. You can only move it along the line of action of that force. So for F1 it can only be moved along this line infinitely anywhere, but I cannot move it any other to, but I cannot move it to any other point. Okay, important to remember that. That also means that if a force is acting, let us say there is this point O and there is one force that is acting in this direction and one force that is acting in that direction. I could bring this force to act from O and this force also to act from O. That is a very convenient arrangement, that is a very convenient notation change that I could make that will make my analysis simpler. So I could not only move it along the positive direction, I could also move it along the negative direction. So although the force is starting here and acting in this direction, I could essentially pull this force and make it act from this point. That wouldn't change the analysis. Right. So according to that, this is a very convenient principle that is used in the analysis of forces quite frequently. Right. Some other examples are given here. So I could, for example, from O, F1 is acting in this direction and F2 is acting in this direction. Right. I could assume this to be, F1 is acting like this and F2 is acting like this. We know from high school vector analysis that these two are essentially the same. Using triangular law, parallelogram law, we know that these things are essentially the same. A question is, how do we resolve forces? We will spend some time on this topic because in future classes I will be writing out immediately the resolved vector while solving problems. So I will spend a few minutes on this topic. Let us assume there is a force F acting in this direction shown. That direction is given by some theta to x axis. The xy axis is this, the xy axis is given here. So that is the xy axis. Anyway, I am writing it again, it is already given here. Is it not? So that is the xy axis. So at an angle of theta to x axis, this force F is acting. Now I would like to know the components of this force along the x and y axis, or I would like to resolve this force into its components. For the purpose of this discussion, I am only doing it in 2D. Remember that force is a vector and it can exist in 3D space, and I could also resolve it in 3D if there is a need, but since here we will be dealing only with 2D for now, I am only solving this for 2D. Okay. So the question is, I have F and I know the value of F and I know the direction at which this F is acting with respect to the x axis, that is theta. These two are known. What is it that is required? I want to know what is the value of F x and Fy, or the x and y components. I would like to resolve this force F into its corresponding x and y components. Why do you have to do this? Because you know F. I know F. What is the point in resolving this into corresponding x and y? Well, you know, in this problem you know F already, there is nothing else, there is no other force that is there. But suppose there is a different problem in which there is one more force that is also acting from O, okay, which I am going to call as some F2. Okay. Now I would like to know what is the total force that is acting, for example, and what is the direction. Now that is not in this case it appears trivial. In some cases it is not actually so trivial. You cannot simply add them because force is a vector. You cannot simply add them. Two vectors are equal only when their components are equal. So it makes sense for me to componentize or resolve this F and F2 into corresponding x and y components and then sum them in the corresponding components and then find the final result, something like that. So this is an expected application, and as you solve problems you will realize what is the use of this. So coming back, what is the problem that we are dealing with? We have F that is known, you have been given F is a force that is acting in theta direction at an angle of theta to x axis. What is asked? I would like to know the corresponding x and y components of this force. This is what is asked. Well, okay. How do I find this? Now for finding the x component fx, consider the right triangle. I know this is high school physics, but please bear with me because there are some students who may be taking it from other backgrounds other than mathematics who may need this refresher. Consider this right triangle OAF, right, that is 90 degrees. In this, the hypotenuse is OF. Okay. What is sin theta? We know sin theta is opposite side by hypotenuse. Since this is theta, sin theta is FA, or rather AF divided by OF. OF is the hypotenuse. Okay. But we know the value of OF, that is the magnitude of the force F, is it not? Okay. That is AF by F, the force in this case. Likewise, I am writing what is cos theta. Cos theta is adjacent side by hypotenuse, that is OA divided by OF, and that is actually OA divided by the magnitude of the force F. We know that the hypotenuse is the magnitude of the force F, and I have told you already that F is given, you know F. Now, what is the question? The question is find Fx and Fy, is it not? Fx is OA, is it not? Fx is OA, and that is actually F cos theta, is it not? Because cos theta is OA by F, that means that OA is F cos theta. So, the component of this force along the x axis is F cos theta. The component of this force along the y axis is OB, but that length OB is the same as the length AF, is it not? It is the same. And what is AF? That is F sin theta. So, by this we understand that the component of F in the x axis is F cos theta for this problem. Okay. Depending on where theta is, this might change. Okay. So, this is not a standard. So, you cannot use this everywhere cos theta, you cannot do that. Okay. Depending on where theta is, as we will solve problems, you will realize that this will change, and Fy is F sin theta for this problem. Now, let us look at an example. Okay. This is the xy axis given, please note this, this is the xy axis that is given. Okay. The question is resolve this force F into its corresponding x and y components. Note, something to note is this bar is at an angle of theta from the horizontal, where the horizontal is the x axis. Right. Now, how do I solve this problem? Well, same principle. It is scary looking, but it is not scary. Right. Same principle. So, what do? I try to find the cosine of 90 minus theta, but why is that? Why do I find cosine of 90 minus theta? Well, because I would like to find that component, right, and that component is the x component, it turns out, that is that component. I am interested in finding that distance, that is OA by OF, is it not, in this triangle OAF, that is the OA by OF, and OA then is OF of cos of 90 minus theta. Note that, why is this 90 minus theta? Is it confusing? Because this force itself is acting at an angle of 90 degrees to this bar, but the bar itself is not horizontal. The bar itself is inclined at an angle of theta to the horizontal. Because of this reason, this angle happens to be theta. Why is that? This is alternative angles. Because this angle happens to be theta, because of that reason, because the total angle is 90 degrees, then this angle becomes 90 minus theta. Okay. So, Fx then is f times cos of 90 minus theta. Likewise, I am interested in finding that AF is sine of 90 minus theta, that distance, this is sine of 90 minus theta times OF, is it not that? Because sine of 90 minus theta is AF by OF. So, that would mean that AF then is OF times sine of 90 minus theta, but OF is the force F. So, the y component is F times sine of 90 minus theta. Let us look at one more example. Now, the question is, resolve the force F along x direction and y direction. How would you solve this problem? So, the directions are given, that is the direction that is given. Okay. Now, I am interested in resolving this force along the x direction and y direction. Now, the horizontal is already drawn for your reference, that is the horizontal, right. Note that the bar is inclined at an angle of 30 degrees to the horizontal, the force is acting at an angle of 20 degrees from the bar. Okay. You can essentially add them to get the angle from which the force is acting from the horizontal, that is 50 degrees. I could get that. Okay. If that is the xy axis, for example, that force is acting at, this is a value of 10 newtons, is acting at an angle of 50 degrees from the horizontal. Okay. Now, I am interested in finding its x component and y component, right? Not. Now, what is Fx? Fx is the component of this force along the x direction, is it not? Along this direction. Now, in this right triangle, the force is the hypotenuse, and I am interested in finding the adjacent side. That means I will have to find the cosine, is it not? So, Fx then would be f cos theta, or 10 times cos 50. I am not solving the numeric, I will leave it for you as an exercise to solve. Then Fy is that distance, is it not? Or rather this, but these two are actually numerically equal, also the directions are equal. So, and according to principle of transmissibility, I could actually move it where I want. Fy is actually 10 times sin theta. What is the direction in which it is acting? That is the question. Because how would you solve this? If I am solving this in this xy axis, for this positive xy axis, then how do I do this is, because this distance is, because this angle is 90 plus 50, I have to say sine of 90 plus theta, I will have to say that and then solve it, because I am interested in finding the answer with respect to the positive y axis. The other way of saying that is simply that it is 10 sin theta in the negative y direction, because this is the direction that I am finding with this. If you use some intuition, this is not too difficult, because that is in the negative y direction, that is minus 10 sin theta. Again, I am not solving the numerics. I request you to please check this, the numerical answers for this problem. So, with this we come to the end of this video. In this video we saw some examples of resolving forces, principle of transmissibility, and forces and the types of forces that are acting on a body. Thank you very much for your attention.